Let's talk about trig identities. We're going to see a couple of different groups of identities, starting with the reciprocal and quotient identities. These are going to seem really familiar because we talked about them as we were defining the other trig functions. From there, we're also going to talk about the Pythagorean identities, which are really similar to a squared plus b squared equals c squared. And we're also going to be using these identities to simplify trig expressions. Let's go ahead and get started with the reciprocal identities. Like I mentioned, these are a lot like the definitions. So I can go through these and I can just rewrite these as cosecant being the reciprocal or 1 over sine theta. Secant is the reciprocal of cosine, so 1 over cosine theta. And I want to write cotangent as a reciprocal as well, and that would be 1 over tangent theta. These can be rewritten in reverse too. So for example, I can write sine theta as 1 over cosecant theta. So there's actually 6 of those if you want to think of it that way. Next are the quotient identities. For the quotient identities, I'm going to write these as a quotient of sine and cosine. Starting with tangent. Tangent is sine theta over cosine theta. And cotangent is the reciprocal, so cosine theta over sine theta. Next, we want to simplify these expressions into a single trig function. One really great strategy is to write everything in terms of sines and cosines. Not always the way to go, but a really great way to start. And we're going to do that very thing with number 1. So number 1, I've got tan theta over sine. I'm going to rewrite tangent as the quotient sine theta over cosine theta. I'm dividing that numerator by sine theta. But instead of dividing, I can think of that, so sine theta over cosine theta, I can think of that division as multiplying by the reciprocal. So if I think of that as sine theta over 1, I can instead multiply by the reciprocal 1 over sine theta. And I can cancel those sine thetas. I get 1 over cosine, which is secant theta. It says a single trig function, so you could leave it as 1 over cosine, but the simplest form would be that secant theta, the secant theta that I've got written there on the answer line. Okay, next I've got secant cotangent. I'm again going to use the strategy of getting my expression in terms of sines and cosines. Secant is 1 over cosine, see our angle is t there, cosine t, times cotangent, which is cosine t over sine t. Oh, this one's nice. I can cancel those cosines. I get 1 over sine, which I can simplify just a little bit further. That is cosecant. So I get cosecant theta. Number 3, I'm going to go ahead and change the denominator into sines and cosines. So I'm going to just rewrite that numerator, 1 over sine t. Secant is 1 over cosine minus tan, which is sine over cosine. I can combine these two fractions in the denominator into a single fraction using cosine as my common denominator. So just rewriting the numerator, no change there, at least not yet. I can go ahead and combine my numerators there. So I get a 1 minus sine t all over cosine t. Let me circle that in red so you can see that that really is just the denominator combined into a single fraction. Now this is a division, so I'm dividing by that 1 minus sine t over cosine t. Instead, let's go ahead and multiply by the reciprocal. So I'm going to take that numerator, 1 minus sine t, and I'm going to reciprocate this denominator. So I'm going to multiply it by, let's put cosine t on top, and then 1 minus sine t in the denominator. And I can cancel these, and I end up with cosine t. So I have a single trig function, and I've simplified that guy all the way down to cosine t. Next, we're going to look at the Pythagorean identities. The Pythagorean identities are based on the Pythagorean theorem, a squared plus b squared equals c squared. I'm going to use this on the unit circle though, so instead of using c as my hypotenuse, I'm going to go ahead and use 1. Let's go ahead and label these legs on the right triangle as A and B. I've got my right triangle there. And I'm going to just choose this corner right here to be theta. The Pythagorean identities are in terms of sines and cosines. So I'm going to go ahead and find sine and cosine from this triangle. So let's go ahead and start with the sine. So the sine of theta, sine is opposite over hypotenuse. So katoa. So opposite is going to be b over 1 or b. And then we'll do the same with cosine. Cosine theta is adjacent over hypotenuse, and that's going to be a over 1 or a. So for this Pythagorean identity, the first iteration of it anyway, I can go ahead and start by thinking of it as the Pythagorean theorem. A squared plus b squared equals c squared. But when I put it in terms of my trig functions, a is cosine, so this becomes cosine squared theta plus b. B is sine squared theta. And c is my hypotenuse, which is 1. Notice I've written that as cosine and then the power 2 and then theta. That's equivalent to taking cosine theta and then squaring it on the outside. It's cosine theta times cosine theta, either way. So this is iteration number 1. There are 3 of them. To get to the other 2, we're going to go ahead and do some dividing. I like to think of these as all being based on that initial cosine squared theta plus sine squared theta equals 1. For the second iteration, I'm going to go ahead and divide by, so I'm going to divide by cosine squared. So I'm just going to work all the way through cosine squared, 1 over cosine squared. This gives me the next version. So cosine squared over cosine squared is 1. Sine squared over cosine squared, that's tangent squared, equals 1 over cosine squared is secant. Okay, so there's another version of it. 1 plus tan squared theta is equal to secant squared theta. For the third iteration, the third and last one, I'm going to go ahead and start with my original function again. Cosine squared plus sine squared. Let me redo that. That's super messy. Sine squared equals 1. Let me get this out of the way as well. But this time, let me grab my green pen. This time, I'm going to divide, instead of by cosine squared, I'm going to divide by sine squared. So I'm just going to run all the way through and divide everybody by sine squared. And I get the third version of this, cosine squared over sine squared. That's a cotangent squared theta. Sine squared divided by itself is 1, and 1 over sine squared is cosecant squared. And there's the last version. So I think the easiest way to remember these, we'll give you a couple of nice ways to remember these, is to always start with the original cosine squared plus sine squared equals 1. If you've got that one memorized, you can always get to the other 2. You can also memorize the second ones because the C's go together. So the cotangent goes along with the cosecant, which leaves the T and the S to go together. They're right next to each other in the alphabet, tangent and secant. So you do want to have these memorized. It's going to make the rest of your work so much easier rather than always flipping and trying to figure out what identity you've got available to you. So we're going to be using those 3 identities, but we're going to be again simplifying expressions to a single trig function as we had up above. So in number 1, I've got 1 minus cosine squared. So that tells me that I want to go ahead and use the first version of that identity. If I rewrite it and I bring the cosine squared to the other side, I get sine squared by itself is equal to 1 minus cosine squared. So I'm going to replace that numerator with 1 minus, I'm going to replace 1 minus cosine squared with sine squared. So this is sine squared. Let's see, these are t's, aren't they? Over sine t. I can go ahead and cancel one of those with the sign in the denominator, and I get sine t. So that simplifies to sine t. Okay, for the next one, I've got cosine t times the quantity tangent squared t plus 1. So if I look up here, I see that tangent squared plus 1 is equal to secant squared. So I can go ahead and replace that with a secant squared. So let's start there. I'm going to leave the cosine. So cosine t times, this gets replaced with secant squared t. Putting everything in terms of cosine, so I can simplify this further, I have cosine times 1 over cosine squared. I can cancel one of those with a cosine in the numerator. I get 1 over cosine t, and that is secant. So this one simplifies to be secant. Next, this one looks a lot like one of the ones we had up above. So I do want to start by getting everything in terms of sine and cosine. Let's go ahead and take that denominator. I'm going to leave the numerator sine t. Secant is 1 over cosine t minus cosine. So this is going to be minus cosine. I want to change that denominator so I can combine it into a single fraction. To do that, I need to use cosine t as my denominator. So I'm going to multiply this second guy, the cosine t, by a cosine t over cosine t. We call that a unit fraction, changing the way it looks, but really multiplying it by 1. So I still have sine t in the numerator, no change there. 1 minus cosine t. I'm just changing the second piece, minus cosine squared t over cosine t. Now I can take that denominator and simplify it into a single fraction. Sine t is still, whoops, I want blue. Sine t is still my numerator. In my denominator, I've got 1 minus cosine squared t over that common denominator of cosine t. Now this is division, and I want to go ahead and change this division into multiplying by the reciprocal of what we have here in our denominator. So as I rewrite that so I can simplify it further, I have the sine t times the reciprocal of what I've circled in red. So cosine t is going to go on the numerator, 1 minus cosine squared t in the denominator. 1 minus cosine squared t, I'm scrolling up here because we had it right up here. It's equivalent to sine squared t from the Pythagorean identity. So I'm almost there. I've got the sine t times cosine t over sine squared t. If it helps you to keep your numerators and denominators straight, that sine t can be written as sine t over 1. So it really is in the numerator. So I can cancel one of the signs in the denominator with the sine t in the numerator. I end up with cosine over sine, which is cotangent t. So I end up with cotangent of t. Okay, number 4. I've got sine squared. That one can go ahead and stay. But cosine squared t minus 1 looks like one of my Pythagorean identities. Let's go ahead and go up to the list of identities. This one has the cosecant in it. So we're going to use this one. Cotangent plus 1 equals cosecant. Let's go ahead and write that down here. So I know that cotangent squared t plus 1 is equal to cosecant squared t, but I have cosecant squared minus 1. If I subtract 1 from both sides, cotangent squared is equal to cosecant squared t minus 1. So I can replace the cosecant squared minus 1 with the cotangent squared. Let's go ahead and do that. So taking this, I still have my sine squared t, and I'm going to replace the cosecant squared minus 1 with cotangent squared t. Let's go ahead and put this in terms of sines and cosines. So I've got sine squared t times cosine squared t over sine squared t. I left an n off there. Cancel your sine squareds and you get cosine squared t, and that is our answer. So as you look back through my strategy, cosine squared t, I was using the strategy of changing everything into sines and cosines, but it didn't happen until my second step. So sines and cosines didn't happen until this step right here, changing things into sines and cosines. It looks like I didn't need it for the last one. We were already in terms of sines and cosines. And then same thing here, I went ahead and used the Pythagorean identity first, sines and cosines second. So thinking through those strategies, sine and cosine second. There's a couple different ways that you can go with the ordering. However, when you're simplifying and you have a sum of squares or a difference of squares, you really want to think about utilizing those Pythagorean identities, one of those three versions. Okay, scrolling down to the bottom of our worksheet, we're going to go ahead and review these common trig values. You need to be memorizing these. You want to be really, really good at these because we're going to be doing problems in the very near future that involves knowing these quickly so that you can do a bigger problem. I'm going to go ahead and start with my quadrantal angles. So I've got several to choose from here. I know that pi is a quadrantal angle. There's pi. Let's look for another one. Pi halves is another quadrantal angle. And one more, 3 pi halves. So 3 pi halves. With those quadrantal angles, because we're on the unit circle, I know that those are all going to be either zeros or plus and minus ones. Let's go ahead and start with the sine of pi. So to get to pi, I travel over here. I land on this point on the unit circle. That point is at -1 for x. So -1, comma 0. We know that the cosine refers to the x and the sine refers to the y. I'm looking for the sine value. The sine value is the y coordinate, so that's going to be 0. Okay, next, pi halves. If I travel pi halves, I land on this point right here that has 0 for x and 1 for y. I do want sine again, so I'm going to pick up the y coordinate, which is equal to 1. See how quick this goes? Sine of 3 pi halves. 3 pi halves lands me over here, 3/4 of the way around the circle. And that point has 0 for x, -1 for y. I'm looking for cosine this time, so I'm going to pick up that x value, which is 0. Next, let's do anything that has a fourth in it. So I'll go ahead and use blue this time. So anything that has a fourth in it, so anything with a pi fourths, I know that my answers are going to be radical 2 over 2's, plus or minus. You could also, if you wanted to, express that as a 1 over radical 2. So it's just a matter of determining where I am around that unit circle. If we review our quadrants, everything is positive in quadrant 1. In quadrant 2, we have negative x's but positive y's, negative, positive. In quadrant 3, everything is negative, negative, negative. And then finally in quadrant 4, we have, now we're back in the positive x's but negative y's, positive comma negative. So this is really all I need to think through other than a tangent. Let's go ahead and start with the sine of 3 pi fourths. I'm going to use the second circle here since I kind of made a mess of the first circle. It's nice to base everything off of 0, 2 pi, and pi. So pi in terms of fourths is 4 pi fourths. I'm not all the way there. So 3 pi fourths is here. So this would be 1 pi fourth, 2 pi fourths, 3 pi fourths. Okay, so there's 3 pi fourths. I could draw in the triangle. It's an isosceles right triangle. My two legs have the same length. I am in quadrant 2, so I know that this is going to be a negative radical 2 over 2, and this is going to be a positive radical 2 over 2. I just did too much, right? I only am concerned about the sign, so I really want the positive radical 2 over 2. radical 2 over 2. Find the next one in terms of fourth. Okay, there it is, negative pi fourths. So to go negative pi fourths, I need to move clockwise, and I'm going to land right here. Again, I end up with my isosceles right triangle. I know that tangent is y over x. It's the slope, right? My y's and x's are the same. So these tangents are always 1 or negative 1. This happens to be on the negative slope. You could work out all of the y values over the x values, but I know it's a negative slope of 1. Let's see, where's the next one? 5 pi fourths. Okay, so again, I'm basing everything on either going halfway around the circle or all the way around the circle. Halfway around the circle is at 4 pi fourths. So I need to go just one more. This guy right here gets me to 5 pi fourths. So traveling there, 5 pi fourths. I again have an isosceles right triangle, but everything's negative in this quadrant. I have a cosine. I better put a negative on that radical 2 over 2. And I think I got all of them. Okay, great. Let's go to our green pen. Now we're going to do things in terms of either a pi thirds, which is 60 degrees, or a pi sixths, which is 30 degrees. These, and it's just going to depend on the order of sine and cosine, these are going to be either halves or radical 3 over 2, plus or minus depending on where you land. I'm going to erase what I have in this first circle, so I can see if I can erase everything but the quadrants. So I'm going to go ahead and redo this in the first circle. Go ahead and draw yourself a new circle if you need to. We're going to go ahead and start with cosine of pi sixths. Pi sixths, that's 30 degrees. So I'm going to end up with this triangle. My triangles are squashed compared to those isosceles right triangles that we saw with the pi fourths. They have a short side and a long side. The short side is always 1/2. The long side is always radical 3 over 2. The only thing you have to change is whether it's positive or negative. This one has the short side over here and the long side on the x-axis. I want cosine, which is the x, so I'm going to choose the longer, which is radical 3 over 2. Next, we have cosine of 4 pi thirds. Halfway around is pi, which would be 3 pi thirds. So I need to go one more. It's a 60-degree angle. Okay, so again, I've got this triangle that has a long side and a short side. This is traveling 4 pi thirds. I want cosine, which is the x again. So I want this side here, which is going to be negative, and it's the shorter side, so it's negative 1/2. Next is the sine of 5 pi sixths. I can think of that pi in terms of sixths as 6 pi sixths. So I'm almost all the way around, but not quite. So that gets me to 5 pi sixths. Okay, so I have a short end and a long end. I want the sine this time, so I want the y value or the short end, which is going to be 1/2. I'm in quadrant 2 and my y's are positive. Okay, next, cosine of 5 pi thirds. 5 pi thirds is almost all the way around. So when I get to 2 pi, in terms of thirds, this is the same as 6 pi thirds. So 5 pi thirds is going to go over here. So I want, what did I want? Cosine. So I want the x side. Let me just pull this off so you can see what it looks like. The x side is the shorter side, and I'm on the positive x-axis. So I want positive 1/2. Let me erase what I've got so far so we can keep going, and it's just getting messy. Okay, next one is negative 11 pi sixths. Well, in terms of sixths, pi is the same as 12. Oh, sorry, 2 pi is the same as 12 pi sixths. I'm going almost all the way around backwards. So it's going to get me to this triangle right here. I want cosine, which is the x. So I want the longer side. Radical 3 over 2. Got one left to go, and that's the sine of 2 pi thirds. So I'm almost all the way to pi, which is 3 pi thirds. So 2 pi thirds is going to be here. I want sine, which is the longer side, radical 3 over 2. Radical 3 over 2. This is a great set of trig functions to practice on. It's got a really nice variety. What I really want you to take away from this is that it really just depends on what quadrant you land in. For pi fourths, you know it's going to be a variation of a radical 2 over 2, either positive or negative. If you land on a quadrantal angle, so you land on one of the axes, you're going to have a 0 or a 1. And if you're dealing with that 30, 60, 90 triangle, you've got a pi thirds or a pi sixths somewhere in there. You just need to decide if you're on the longer side or the shorter side. And that gives you the choice between the 1/2 and the radical 3 over 2.